All right. Welcome back, everyone. Hi, Verge.
Hi, Mark. Welcome, everyone, to our 20th AP Live.
All right. I guess I have to advance the slide for it to advance. All right, there we go.
I love these transitions.
I am Mark Corelli from Ryan High School in Denton, Texas.
And I'm Verge Cornelius from Lafayette High School in Oxford, Mississippi. We were just on Google Maps with our producer showing us how close we really are. Like, you can actually drive from our one house to the other in 8 hours, which going 70 miles an hour, which you can do in this part of the country. So not going there anytime soon, but
yeah. Yes, we got an email from Upper Peninsula, Michigan today too, and I've got a nephew and his wife just graduated from Michigan Tech, so I was looking at Google Maps on that too. Very useful. All right, so this is what we're doing, right? And hopefully our pictures are not covering up the QR code like I think they may have been yesterday, but this is where we're headed, where we've been if you haven't watched the old videos. But we are down here on April 21st, and that QR code will bring up a bigger version of this if you want to see where we're headed.
All right.
And where we're really headed is May 12th at 2 Eastern to the AP Calculus exam, which will be 45 minutes and online. And I think everyone's gotten this information already, but if not, you can check out apcoronavirusupdates.collegeboard.org.
And we're going to know more information about what that upload process might be and everything sometime next week. And you will too. I think they're going to send out some videos.
Yeah, I think the 27th, the latest, which would be a week from yesterday, right? All right. And we just introduced this picture yesterday. And it's gone.
Yeah, luckily, we have a lot of pictures of us together.
Pretty soon you're going to start seeing our faces photoshopped over great, Thelma and Louise going off the cliff or something. And this was just a rush thing. We were rushing at the end, and Verge was trying to throw you a little more complete answer, and I wasn't checking it because I was getting the slideshow ready. And that, which points the change from increasing to decreasing and decreasing to increasing at, got flip-flopped. So
if you didn't catch it, then you might want to go back and watch it again. Or if you haven't watched yesterday's video at all, you might want to watch it also.
And it was right at the end, and the only messages we got on it were from friends. So I figure people either figured we'd catch it or they'd tuned out. All right, so introductions and corrections / banter are over. We're about to do our warm-up. In today's Unit 6 review, integration and accumulation of change. We're going to bring in a little bit of Unit 5. We may touch on, we may push some of this off into tomorrow. Unit 6 and Unit 5 have a lot of stuff in them. And as far as the further resources go, I forgot to mention this yesterday, but Sunday afternoon, Thursday and Friday's keys went up. So everything, all the keys that you're going to get from us are in the Dropbox for last week. Tomorrow I will put Monday's key in, and we'll kind of have a 2-day lag there on everything. All right, here's our warm up. I'm going to move my little unseen chat box in our images so I can see the graph. It says this is actually number 5 that we ended on yesterday, that problem that we had the correction on. This is part D, which we had snipped off, and now we've snipped it back in, right? It says the figure above shows the graph of f prime, the derivative of a twice differentiable function f on the interval from -3 to 4. The graph of f prime has horizontal tangents at x equals -1, x equals 1, and x equals 3. The areas of the regions bounded by the x-axis and the graph of f prime on the intervals -2, 1 and 1, 4 are 9 and 12 respectively. Given that f of 1 is 3, write an expression for f of x that involves an integral. Find f of 4 and f of -2. All right. And there's a little bit of new information. I think, did you cut it off yesterday or did you just cross it off?
I crossed it off as I was reading it yesterday, and it had to do with the areas of the regions. So yeah, okay, that was the part I had crossed off in purple, and Mark has it underlined now. That information is very important to answering part D, and he in fact put up in the figure the 9 and the 12. So
yeah, so I am going to actually switch over to my camera to help work this in a second, but let's let people read it. If you want to pause it. And normally we do something to cover some time.
Okay, that's called a joke. I have a plethora of new jokes that people have sent me, people who I don't even know and people that I do know, and lots of double jokes and some jokes that we've already told. So that tells you something. But anyway, lots of jokes that we haven't already told. So this one is really good for today's review lesson. And the question is, what's the integral of 1 over cabin with respect to cabin?
So decabin over cabin.
Mm-hmm.
Can I answer, or do you want to go ahead?
Go for it. Of course you can answer.
I believe it's a houseboat.
You are correct. A lot of people would say log cabin, but then they'd be forgetting what?
The sea.
Yeah!
And a log cabin on the sea is a houseboat.
That's right. So we'll kind of come back to that later in the lesson. Okay.
All right. So, here's a slightly off-kilter version of what you just saw. All right. So same information, maybe arranged slightly differently for the margins, but we've got from -2 to -114, and I labeled those up here. And it says we're given f of 1 is 3. Write an expression for f of x that involves an integral. So, well, where's 1, right? Here's x equals 1. And they mentioned 4 at first. So my bounds have to be x values, and the only two x values they've mentioned are 1 and 4. And if I integrate f prime from 1 to 4, I'm going to get the bounded area. But what do we know about f prime in that interval?
It's below, f prime is below the x-axis, so the bounded area is actually going to be negative in sign, SIGN.
Yeah, so if I wrap absolute values around this, it equals 12. But that integral equals -12, because that Riemann sum or definite integral, which a definite integral is the limit of a Riemann sum, foreshadowing, is equal to those areas, which sum to -12 in this case, if we have signed area, SIG in the so that equals -12. Now they want me to find an expression for f of x, though. So f of x, this is, if you guys don't remember, this is where the review comes in, right? And we did this last week, and we touched on this. The fundamental theorem of calculus. One of the two versions of it. The integral from a to b of f prime of x dx is f of b minus f of a. So if I want to find f of b, and this is actually the way I straight memorize it as the accumulation model, but tomato, tomato, no one says tomato. All right. F of b is f of a plus f prime of x dx. Well, the f of a that I know is 3, and that goes with the 1, because f of 1 is 3. This is my a and my f of a. And I'm trying to evaluate x. Now, this is where people will get picky. I'm going to put that in terms of a dummy variable t. And I will leave it to others to discuss whether x's can change the meaning there or not. But traditionally, we put a dummy variable there, because when I antiderive that, when I differentiate that, I'm going to plug in an x and plug in a 1, and then I'll have a function in terms of x.
And because they said write an expression, you didn't even have to write the whole
That's
equation.
right.
You
I could have just had this.
Yeah.
Good point. That's actually because they told me to write an expression for f of x. So the expression I put would be an expression for f of x. And then they want me to find f of 4. So now I'm going to do 3 plus the integral from 1 to 4. And now you see where, okay, f prime of x dx is -12. Well, f prime of t dt is also going to be -12. So will f prime of q dq, right? So -9. And f of -2, well, now I just get to plug things in, although that seems deceptively easy. All right, the integral from 1 to -2. Wait a minute. Thought bubble time. How would I normally find this area?
I would really usually do like integral from -2 to 1 of
Yeah.
f prime, and we know that
And,
that's also negative. Mhm.
and that will equal -9. But in this case, when I reverse the bounds,
This is one of the properties of definite
that's
integrals.
right,
It becomes
all
opposite.
kinds of parentheses. Wah, 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 wah. So we're going to add the opposite of the integral, which is -9. You could also switch this first if you wanted to, right?
Mhm.
Or if you just use the fundamental theorem up here, you could do the integral from -2 to 1 equals f of 1 minus f of -2, and then plug things in, and that'll
Mhm.
work the subtraction out for you as well. But
Mhm.
I believe you get 12 as long as you do it right.
Yep. That's what I got.
Good.
So in the shared folder today, um, there is a notes template. And so I'm going to go ahead and grab the screen and do
Yeah, please do.
some of the notes with everyone. And then Mark's going to do the rest of the notes with us. So I think that's how it's going to go. I always, those of you now watching, I do this every single time. It helps me remember what day it is. And we have tacos on Tuesday. So I don't know why, but we have tacos on Tuesday. It's a thing. And it's our Unit 6 review. As Mark alluded to, Unit 6 is long. When I taught Unit 6 back in, I don't know, January, I actually called it Unit 6 and Unit 6.5 because like we had to have a test before we started U substitution, you know what I mean? So these are just really the highlights. And so we're going to continue to revisit a lot of these ideas as we get closer and closer to May 12th. Okay, so this example right here on the notes template is exactly the same example from yesterday that we did on our notes template. The exact same graph, the exact same given information,
Although I
but
think you changed the name. I think it used to be G. So.
okay, I renamed it. Yeah, that was the graph of a differentiable function h of x now is shown below on this closed interval from -4 to 4. The function h of x has x-intercepts on the interval from -4 to 4 at x equals -3.8, x equals 1, x equals 0, and x equals 3.4. So those are those x-intercepts right there. And also h of x has horizontal tangents at x equals -2.9. So right here, I feel like it's like Groundhog Day or something. I feel like I did this yesterday. X equals -0.5 and x equals 2.2. Oh, but here's some interesting stuff. The areas of the regions bounded by the x-axis and the graph of h of x on the intervals from -1 to 0, 0 to 3.4, and 3.4 to 4 are 0.3, 12, and 2 respectively. So let's see. This is going to be 12 right here. And then I'm going to do Mark's little sound effects, 2 right there. And then this little teeny tiny hump of area is 0.3 right there. So I don't know anything about this area or this area. And I don't need to because I'm not going to ask you about it. So, all right. For all x, g of x is equal to 11 plus the definite integral from 0 to x of h of t dt. So now I have an equation that is relating this g function and this h function. So that's kind of interesting there. We have to find a bunch of different stuff. So the first thing we have to find is g of 3.4. How would I do that? Well, Mark just said on the warm-up example, we'll just plug it in. So we're going to say g of 3.4 is equal to, so I just plugged in the 3.4 there, is equal to 11 plus the integral from 0 to 3.4. So I'm plugging in for x and for x of h of t dt. So that's that dummy variable, and that's really what mathematicians call it. Mark wasn't making that up.
It's just stupid.
It's like a placeholder, I mean, it doesn't matter. It could be any variable, u, t, you don't want to pick x. That's really subject of a much later class, but to be mathematically correct, you do need to have a different variable there. All right, so 0 to 3.4 of h of t dt. This is 0 to 3.4. This is -12. So in this G of 3.4 ends up being 11 plus negative 12, which is negative 1. Unit 6 is all about what the integral tells us. It's about accumulating area. It's not necessarily about rate of change. There's no doubt we're going to be taking some derivatives, but I just kind of had that accumulation function. I was able to evaluate it. G of 4 is going to be kind of similar here. So G of 4 is going to equal 11 plus, and I'm just going to kind of scoot over. Who wrote this thing? I guess I did, didn't I? 11.
What I'm doing in the background right now, I'm actually on my drop. I'm actually in the Dropbox. Because
don't flip out on us, Mark.
No,
you don't.
That first H is not in italics, and it's driving me crazy.
This one. Okay, so that'll be fixed.
So it's already fixed. I just have to upload it. So.
Okay, good. Thank you. All right, so G of 4 is going to equal 11 plus the integral from 0 to 4 of h of t dt. Okay, so the integral from 0 to 4 of h of t dt is going to be negative 12 and then plus 2. So this ends up being 11 plus negative 12 plus 2. You could have also kind of stolen from here and said negative 1 plus 2 if you wanted to. In any case, you get positive 1 for that answer. Okay, G of negative 1, I'm going to go ahead and bring it up over here. G of negative 1 is going to be 11 plus the integral from 0 to negative 1 of h of t dt. And this is my graph of h. I'm trying to figure out the area. Oh, but these limits of integration are what I might call backwards. A lot of times we want to see that lower limit on the bottom because that'll tell us correct information about the areas and things like that. So if I do switch to put that negative 1 on the lower limit there and 0 on the upper limit, I need to change that to a negative. So I have 11 minus the integral from negative 1 to 0 of h of t dt, which I was told was equal to 0.3. So I have 11 minus 0.3, which is, I believe, 10.7.
I believe you're correct.
Okay. Next one, g prime of 3.4. Ooh, now it's getting good. So g prime of 3.4, I've got this equation right here, and I need to take the derivative of it. Okay, let's see what I do here. I might, in fact, I don't know, do something like this just to give myself a little bit more space to explain what's going on. So g of x is equal to 11 plus the integral from 0 to x of h of t dt. If I differentiate on both sides, and now some of you have been with us ever since the beginning, like March 25th. And so we've already done quite a bit of this, you know. For those of you who are just joining us, we haven't really talked about fundamental theorem of calculus or anything, but here we go. We're going to talk about it right now and on the next page as well. But the derivative with respect to x of g of x is going to be g prime. And then here the derivative with respect to x of 11 is going to be 0. I'm not going to write it down. And then plus the derivative with respect to x of this expression right here, the integral from 0 to x of h of t dt, just becomes h of x. That is fundamental theorem of calculus, that when you take the derivative of this definite integral, as long as that lower limit is a constant like 0 or 3 or 1 or whatever, you get this integrand. It gets stepped up a little bit with chain rule, and we're going to see some examples of that today. So here's the thing, is that g prime of x is equal to h of x. So if I want g prime of 3.4, what I really want, based on my given information, is h of 3.4. And h of 3.4 was actually 0. That was one of my x-intercepts. So I know that this answer is 0. So now, when we have to find g double prime of 2.2, it means that I need to take the derivative of this little equation right here. So g double prime of 2.2, I would figure out, g double prime of x, therefore, is equal to h prime of x. So g double prime of 2.2 is the same as h prime of 0.2? Well, this is the graph of h, so h prime, what feature of the graph would I be thinking about? Mark?
So we're looking for the derivative of h, so we're looking for the slope of the tangent of h. You have
Exactly.
a graph of h.
I have a graph of h, and I know that at 2.2, I have a horizontal tangent.
Yeah, that was given, right?
Yeah, that means the slope of that tangent line is how much?
0.
Yep, zero.
Zero.
Exactly right.
Nothing.
Exactly right. And I have the right answer with the right reason and the supporting information that goes with it. A lot of times you do a ton of work. I don't know, Mark, do your students say this? We did all that work and the answer was 0? You know, they get really mad about it. But then they get really mad about having an answer like negative 144 over 26 or whatever, you know?
How am I supposed to recognize to stop at 2 plus 4 over the square root of 3?
Yeah. Okay. So then, you know, given that we're doing this integration and accumulation of change, I thought about the fact that, you know, back in Unit 5, we were supposed to really visit that extreme value theorem. And the extreme value theorem is really what's coming into play in this part B here. It says find the maximum and minimum of g of x on the interval from -1 to 4. Explain your answers. So I'm not talking about the entire interval. I'm just talking about this sub-interval from -1 to 4. So to figure out a maximum or a minimum, I want to check a couple of different places. I want to figure out where g prime is equal to 0. And I want to also check my endpoints. I might also check another place, right, Mark? But that doesn't actually exist in this problem. And that would be where g prime doesn't exist, but the original function is defined.
Right.
Okay, but that's not, it doesn't pertain here because this function is differentiable. So anyway, all right. So let's see, my endpoints are -1 and 4. So g of -1, I usually make a table. Do you mind if I make a table, Mark? You didn't make a table when you were,
at all.
you did on the answers, which you will not get for a few days, but on the answers, Mark
I
didn't make a table.
actually may retype it as a table. It was
Okay.
what I was doing was listing the ones we'd already found, and it
Mm-hmm.
turned out that we'd found them all.
Yes.
I was going to import them into a table, and then I realized, oh, I have everything. So.
Right. Right. You know, okay, I just have to say that this problem took me a really long time to write yesterday, but it gets at a lot of different ideas, and I wanted to have problems that were a big bang for the buck, basically. You know what I mean? Like it's getting at a lot of different ideas. So yes, all of your work's already been done. So you just need to figure out like what was g of -1? Well, g of -1 ended up being 10.7.
I really
That
appreciate you trying to get your bang for the buck, but I want to remind everyone that these videos are free. Actually, that's not true because you all paid for your exam. So I mean, I know there's money exchanging hands, but the amount of your money that's going to this is very small.
Yeah. Okay. So when I say bang for your buck, I really mean like, you know, and I think as a classroom teacher, you know, you only have a limited amount of time with your students. So you want to pick examples that are rich and
Oh yeah,
explain things from multiple
I know you
perspectives.
meant return on value for your own time, but it just
Exactly. Because time is money, right?
yes.
Okay. So at 4, the other endpoint of this interval, g of 4 is 1. I figured that out. And then let's see, are there any places where g prime equals 0? Well, g prime is equal to
I see
h.
one of them,
Mhm.
right? I see one of
Yeah.
them up in the table.
Again, g prime is equal to h. And so let's see, g prime is equal to 0 at 0 and also at 3.8.
It's also your list
So I
of
think
it's also your list of x-intercepts, correct? Up in the paragraph. You can use the graph or you can use the given information.
true. I said 3.8, but what I meant was 3.4, I think, right?
Yes.
Okay. So let's see, g of 3.4 was -1. Yes?
Mhm.
Okay.
Yes.
Yep. And then g of 0 was, well, we never did find that, did we? Huh.
No. but it's a pretty easy one to find.
Yeah, g of 0 is 11 plus the integral from 0 to 0. If these limits of integration are the same, then you're not going anywhere. You're not accumulating area. So this result would be 0. That's not because these limits are 0. It's because the limits are the same.
It's because
So
the width of the
anyway,
interval is 0, right?
yeah. So 11 plus 0 is 11. So let's see, my max value is 11. And then my minimum value is -1. But it's important to check the endpoints, because if you don't check the endpoints, that's the exact time when an endpoint ends up being the answer.
Well, and also if it's saying to explain your answers, you have to explain why you ignored the endpoints if you did, because they were definitely candidates.
Yeah, and there are ways to explain it, but it's actually easier to make a table
Absolutely.
than to do the big old explanation.
Also, just was going to say, when I did this, and this I probably will leave on the key, I reported the maximum value as g of 0 equals 11.
Okay, because that's the way you're showing where it's
which is
occurring.
just another way of saying it. Yeah, but the y value is that maximum or minimum value. So you do not want to record 0 or 3.4 as they're the location of the max and min, but not the max and min.
Mm-hmm. In fact, I don't even have to use the word value here. We took it out from when we were working earlier, but I could just say max is 11 or g of
always go back.
11.
I was just saying, always go back and check the question though, because if they asked for the location of the maximum, now it's 0, right?
Okay. So this next set of exercises is a biggie in Unit 6, and that's approximating areas with Riemann sums. And a lot of times we actually need to demonstrate that we know how to do this, give a table, necessarily give an equation or a graph. So this particular problem reads like this. Little is known about the function v of t except selected values given in the table. Use and then there's 3 different kinds here. Sum with 4 subintervals indicated by the data in the table to approximate the definite integral from -2 to 10 of v of t dt. One thing I always check is that those are actually the endpoints of my given information. Sometimes it's not. Sometimes
That's
it's
right.
like, a little in between. And then I also look at my widths. Are they uniform widths? No, they're not. So I have to be really cognizant of the fact that, like, on this interval, I've got a width of 3. On this interval, I've got a width of 5, and that kind of stuff. So a left Riemann sum means that we are going to take the heights or the y values that are on the left-hand side of the interval. So this interval right here has a width of how much? 1 minus -2 is 3. And then times, we want to take this height right here on the left-hand side of the interval, times 3. Plus, and then the next interval is from 1 to 6. Let's see how this erasable pen does on the printed paper. It's not usually the greatest. From 1 to 6, what's the width there, Mark?
6 minus 1 is 5.
And what about on the interval? Which height do I want, the 4 or the -9?
We are doing a left, and 4 is on the left.
Yep. And then we proceed in this manner between 6 and 7. Now I have a difference of 1, and my height is
the
how much,
9.
Mark? Yep. And then on the last part,
I would just be doing a Technicolor vomit in color with this right now.
Yeah.
if I was doing it. And then let's see, your last one.
From 7
3.
to 10. And then this 2.
And also, the other thing to double check, like Verge has done a really nice job of walking through it step by step, but after you have those 4 products there, and you do want to show the 4 products, we know a lot of you can do these in your head, but you were specifically told to use a sum. And so they're going to want to see a product and a sum in the free response. The long directions to the exam say show the computations that lead to your answer. But if you look, there's 5 possible values of V. And if you look at the left 4, 3, 4, -9, and 2, those are the ones that line up in her 4 products. So that's just a quick visual check after.
And you don't, and we've talked about this before, but you don't have to simplify this. I'm just going to tell you because we already did it earlier today. If I can find my answer, we got 26.
Yeah.
So
the two nines cancel, so it's just the 20 and the 6. Right?
Yeah, just for completion of the notes, I'm going to write that there. Now for the right Riemann sum,
could you put an equal sign in front of it for me?
I get very nervous about
I know, but
linkage.
I think it's times the 3 and the 2 right now.
No, it's not. It's a
Okay.
box. Okay. On the right Riemann sum, we're going to be pulling the right-hand values, but the widths are going to stay the same. So I don't need to, I've already been careful about my work. So I know that all my widths are still the same, but now I want to pick this right-hand 4 plus, and now this right-hand -9 plus, and then the right-hand 2. And then finally, the last one's going to be 0. And when we did this one together earlier today, we got -31. What's really cool is that if you need a trapezoidal sum, you don't need to memorize a formula. Just figure left and the right and average them. I was a math major undergraduate. Mark, I think you were too. And I never knew about the fact that you could do that. Like I didn't even think about it until a student pointed it out in class one day, like recently, like last 10 years, I'd say. And I was like, wow, that's so great. I love it. So anyway, you can go ahead and do that for the trapezoidal.
And if you don't believe us, the proof is left as an exercise for the math majors.
Yes, that's right. It's especially useful when you have unequal widths, and that the AP style questions tend to be pretty creative like that. And you will probably, if you see a table, chances are the widths are going to be unequal. The other thing is the other kind of sum for which you're responsible is a midpoint sum. And we did at least one of those in the Unit 8 videos. And then we're going to definitely revisit tabular stuff and things like that. But if you're curious about how to handle a midpoint sum, this data doesn't lend itself to it, but you could definitely search those videos.
Yeah,
Mark,
I was going to just add to that if you look at, we have that schedule up and it's in the Dropbox. So if you don't have the link straight to the calendar, just go to the Dropbox. It's in the top level. You will see that tabular FRQ is a whole day that we have planned. So
that's true, because it is one that tends to show up. All right, Mark's going to do 4 and 5, but I'm going to go ahead and do this example 3, fundamental theorem of calculus. The actual fundamental theorem of calculus, which you can do a Google search for, or you can look in your textbook or look in your notes. You can find the fundamental theorem of calculus pretty easily. I'm just going to show you like 2 ways in which it would show up. This one right here, the integral from 4 to 9 of 1/2 root x dx. What this is saying is that if I know the family of functions whose derivative is 1/2 root x, I can just hop straight to evaluating this definite integral. And this is something that my students have memorized. You can do a little bit of reverse power rule and rewriting that square root of x, but that would have been the family of functions. And then we would evaluate from x equals 4 to x equals 9. So this ends up to be the square root of 9 minus the square root of 4, or 3 minus 2, which is 1. This is where you see fundamental theorem like 90% of the time in calculus, evaluating definite integrals. Occasionally you see it in this situation where you're taking the derivative of an integral like we did in example 1, especially when you're trying to figure out the relationship between 2 functions. But the one in example 1, there was no chain rule involved, and chain rule is everywhere, right? So we have to do one with chain rule. So this is the derivative with respect to x of the integral from a, so there's my a, and I guess on the side I could say a is a constant, but I actually don't think that notation is necessary. From a to x cubed of this quotient 1/t squared plus t minus 5 dt. This is, sub it in, put x cubed in to each of these t spots, and then multiply by the derivative of x cubed. So this becomes 1/x cubed squared plus x cubed minus 5, and then times the derivative of x cubed, which is 3x squared. If you feel the compulsion that you need to clean this up, it would be 3x squared over, don't mess this part up, x to the 6 plus x cubed minus 5. Power to a power, back to algebra 1. 3 times 2 is 5, not 5, not 5.
Not
I see it
today.
as 5 all the time.
That's
Either
why we
one-
don't simplify on the exam.
Either one of these would have been joyful answers. So,
Verge, if you want,
yeah.
just go ahead, state A has to be greater than 2,
Okay.
because that denominator actually has 2 zeros.
Oh,
So
that's nice. Yeah, because otherwise you'd be like
yeah,
trying to hop over an asymptote.
the discriminant's the square root of 21, and 1
Okay.
so that'll scoot us over far enough that we don't have to worry about those.
Yeah, because then you'd have an improper integral or something, and that's like
Right.
not subject of our
That's
curriculum.
BC.
Or yeah, exactly.
It actually
Thank you, Mark.
They would not be that subtle, I think, on BC. Hopefully.
Yeah.
All right.
You're gonna do the 4 and the 5?
Sure.
Okay.
Feel like it's
So go ahead and steal the screen. I think you'll do them fast.
Screen stolen.
Okay.
All right. Hopefully it's full size for you.
Yep, looks great.
All right. So example 4, properties. I love these problems. If Verge hadn't
That's
put
why
these in, if Verge hadn't put these in, I would have written these. Properties of definite integrals. So given that the integral from 3 to 6 of f of x dx is 7.5, the integral from 5 to 3 of f of x with respect to x is 2, and the integral of g of x with respect to x from 6 to 3 is negative 12. By the way, you may notice I move my prepositions around. I do that intentionally. I think it's fun in math
they can
that
be read all those
as long as the
ways.
prepositional phrases stay intact, you can generally get away with it.
Mhm.
All right. So we have this integral from 5 to 6. You'll notice there is no 5 to 6 here, but I do have 5 and 3 and 3 and 6. So I'm going to take that integral from 3 to 6 of f of x dx, and I'm going to break it up. And I can break that up as the integral from 3 to 5 and the integral from 5 to 6, which is what I'm actually trying to find. And I'm going to zoom in so I can, let's see. By the way, zooming in, if you didn't notice, is a physical motion.
I think actually it looked fine, but it's okay.
It's all right.
You're good either way.
All right. So the integral from 3 to, I'm just worried about phone people.
Turn your phone sideways.
I can't remember who it was. I was watching one of those things from the Saturday night at home concert, and somebody had recorded them. I think it may have been even Paul McCartney had done himself vertically, and I was like, oh, come on, Paul. All right. We don't have the integral from 3 to 5, but we do have the integral from 5 to 3. And this goes back to the problem that Verge let me do earlier, right? That the integral from 5 to 3 is just going to be the opposite of the integral from 3 to 5.
And that's true for any a to b.
That's right. So now, there's the sound effects again as I kill time. All right. So we have negative 2 plus the integral we want equals 7.5. Add 2 to both sides. Integral from 5 to 6 of f of x with respect to x is 9.5. Hopefully that's the answer we got earlier.
I'll check.
Okay.
That's what I got.
Okay.
I got that.
So 3 to 6 was just 7.5, right? Gotta read. All right. Oh, well, heck, I just spent a lot of time talking about this. So that's going to just be the opposite of that, which is the opposite. I can perfectly fine to stop there, but we know that's 12. Oh, good. That leaves me lots of room for C.
You're going to need it.
All right. Now, inside C, what do we got there? Better scoot that over. The integral from 3 to 6. Can I do this with still having my other information there?
Yeah, I can. You can see it.
The integral from 3 to 6 of 4 times f of x minus 2 times g of x plus 4. Well, again, these are all just Riemann sums, and I know you're like, what? These are related to those rectangles. But it's a summation. You know, this elongated s here is a summation. So I can break off pieces. And not only can I break off pieces, I can factor out constants.
Ooh, that's clever.
So this is 4 times 3
Oh, I thought
to
you were
6.
going to take a 2 out of the whole thing.
Ooh, that is clever. I'm not that clever. I'm just going to individually go ahead and do 4 times the integral from 3 to 6 of f of x with respect to x. And then I'm going to subtract 2 times the integral from 3 to 6. I am not distributing the summation notation. I am breaking it up into separates and then factoring the constants out front. And I know you're like, what's the difference? And it's like, well, it's important to someone. So, and then the integral from 3 to 6 to 4. And I could have put the 4 out and I could just have the integral of dx there. And then there'd be an understood 1. 3 to 6, that was given. So we have 4 times 7.5. 3 to 6 of g, well, we just found that in part B, right? So that's 12. And I will be honest, I try to train my students to do this. I doubt they do. So if you want to come up here in the thought bubble, oh, that thought bubble is right behind my picture. So I could do a thought bubble that's 4x from 3 to 6, and then that's 24 minus 12. But when it's constant, it's a rectangle.
Yes, I think it's important. My students right now who are listening are going to say the same thing. Like, we got into Unit 6 by thinking about a lot of physical areas that we actually knew the formulas for before we learned anything about the definite integral. So they would hopefully see that as a rectangle where the area is 12.
Right.
Yep.
And so this is my thought bubble. It's like some people are going to go up here to this thought bubble.
Sure, that's
but
fine.
It's a rectangle of height 4, width 3. 4 times 3 is 12.
The issue is, and this often happens on multiple choice, which you guys aren't going to have to deal with multiple choices here. A lot of times kids will do lots of great work, but then add 4 instead of adding 12. And guess what? It's a multiple choice answer. So this year, that's not an issue for you guys, but you still want to get the answer right anyway. And be careful about that kind of stuff. Yep, great.
I don't think I've had a chance to talk about McBob answers yet, so I'm going to slide that in there. So this is your free response answer. McBob is multiple choice, or when you're trying to match the back of the book.
You know, it could be the circuit also.
Yes, that's true. Oh, so I guess we could call it a McBob C.
Well, or it could be a CT McBob. Yeah,
like we're doing an antiderivative. Let's go ahead and have the C. It's McBobbing on a river or something. The sea.
Oh, look at this set of integration blast. I see that 3 of them are kind of similar and one of them is different.
Speaking of integration blast,
what kind of category?
You put this in here, and I don't know if you know this. I actually have 3 or 4 like blast worksheets that are all like this idea.
I mean, so like. I mean, teaching students integration is a lot of times about recognizing what it is you're looking at, but I don't see but one definite integral in this bunch. These are all indefinite integrals. Yeah.
And Verge said I was going to do these fast. I did that one while she was talking. And it's really easy when you're like, ooh, sine, cosine. But the derivative of cosine, like all cofunctions, is negative. So I need that negative to show up. And you could also do this as a u to u of some strange sort. But then that negative is the one that survives, and the negative sign becomes cosine. You guys know that one. That was just to warm me up again.
This is a great time to, revisit your yellow sheet as well, especially for all the basic antiderivatives. And we actually have a circuit in the shared folder today of some basic antiderivatives, which would be great to work on in the next day or 2.
All right. So I'm going to talk about this the way my students would hear me talk about it. Hopefully it'll ring some bells for you guys. It might be slightly different. That's fine. We're all doing the same math. But the first thing I tell my kids to look for is, can you simplify it? So like if this was a minus, could I factor and cancel? I can't. What's the chain of the denominator? And this is thinking, is u to u an option? And the
2x.
derivative of the denominator would just be 2x, and I'd have this constant. So we're going to break this up, because unlike denominators and the song, breaking up numerators is not hard to do. And I'm going to keep the negative with the x for now, just for some clarity, but I'm going to end up moving it. So I'm going to break it up. And the reason I do that is this should be setting off those Pavlovian bells.
Boop, 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 boop,
of that is just arctangent of x, or the inverse tangent of x, if you use the inverse notation. And then this second one. And you could do this, like I alluded to, as u is 1 plus x squared, and then du is 2x dx. I'm just going to slide a 2 in here. I'm actually going to slide a positive 2 in. And I'm going to offset that by multiplying by a negative 1/2 out front. So that's still my negative x over 1 plus x squared. But now I have derivative over function. And I hear derivative over function as a log, kind of like d cabin over cabin.
Mm-hmm.
That
Don't
negative
forget the
half is still
C.
out front. And then don't forget your constant. Yep. So that was a little trickier, but again, this is for review, and hopefully that's just reminding you of some things you've seen in the past.
And great conversations for students and teachers to have.
And I
when
know
they
it's
virtually.
1:45, but neither of these is going to take very long. So let's go ahead and click them out.
I think so too. Yep.
This is
We've been
2
really,
minus
really
G.
conservative with our time. So
now we're buying it back, right?
we're buying it back.
Yeah.
Yep.
And Verge commented on this the other day.
That was this morning.
No, this was something you commented on the other day. Wait for it. What is the chain of 2 minus G?
A -1. Well, with respect to G, yeah.
Right, with respect to G. So that's my UDU or chain rule, but I left that space there, and that's what you'd comment on the other day, that we kind of, because we can think ahead and know where it's headed, we sometimes deceptively do that. -2/3 plus 1, just a turd. Then dividing by a third is multiplying by 3. And we get -3 times 2 minus G to the 1/3. Of course, you can rewrite it as a cube root if you like. You could also put the divided by 1/3 as divided by 1/3 if you wanted to leave it that way on the AP exam.
And I think one last comment about that one is a lot of students will by accident do a natural log for an antiderivative, and that's danger zone. So when we continue to practice, you will see what we're talking about, because I will continue to insist that we do this kind of practice to at least get a lot of us better at knowing when we do a natural log and when we don't.
Yeah, and this is kind of my fail-safe is derivative over function is a log. This was derivative over function to the 2/3, and that's dramatically different. Okay, and you've seen a variation of this one already in our videos. I believe that we have -3 to 3, but I plug in 5, I get 0. I plug in -5, I get 0, because this is not one that we know how to do in AB with AB techniques.
Yeah,
Except we do. It's just a different technique, right?
It kind of looks like a U substitution, but then we're like, where's the D? Where's the DU?
Yeah, and it turns out that we can't do this with we can't get the closed form antiderivative with AB methods, but we can draw a semicircle. And just like my rectangle up on number 4C, I can find the area of that rectangle as 1/2.
You can find the area of the semicircle.
Semicircle, right. 1/2 of pi r squared, or 25 pi over 2. So that's that area, which is that definite integral.
How come you didn't put a plus C there?
Because it's definite. If I did it, now the one is the fundamental theorem ones are the ones where you're like, where's the plus C? But there's a plus C on both plugging in the B and plugging in the A and vapor. One of the things I do, and this one didn't lend itself to it, I always say when you take the antiderivative, you always have to write a little bit more. And sometimes it's the plus C, and then sometimes it's that evaluation bar. But you never just write the antiderivative and stop writing.
Good point.
And then, of course,
if you don't get that joke, if you don't get that joke, don't worry. We'll explain it more later. Okay, he's explaining it now.
Very short explanation. All right. We need to go back to our thanks for watching slide. So that's coming up. while we're doing that, thank you for coming. Yes, absolutely.
Yeah, and big shout out to all the AB calculus students, and we probably have BC ones watching as well. But we have one of the longest like view times per view of anyone, and you'd be embarrassed to know how long that is. But it's actually like 17 minutes or something like that for the.
Oh, I
I
thought it
don't
was
know.
9.
No. Okay, but when they're watching live, it's longer.
Oh, right. Okay.
Yeah,
Yeah.
like
And we do have a theory that we know there's teachers out there doing a quiz for my backgrounds. And yesterday I lasted a long time before I changed the backgrounds.
that's probably what it was. That's
Yeah.
true.
But yes, and thank you. We do get emails. We've gotten some amazing artwork, and it's so cool. We're hearing from all parts of our country. We're hearing from outside the country. Got an email from Canada yesterday. So thank you for watching, and it's a pleasure to do this for you.
Oh, I was gonna say one more thing. Other groups have celebs showing up, like AP Language got to have Tony, whoever he is, show up. What was that
Hale, I
guy's name?
believe. Yeah.
Yeah.
I
So
think
like
he's the son of the skipper from
I
Gilligan's
told our
Island.
producer we need a celeb, and so our producer was like, you know any celebs? And I was like, I know calculus celebs. I don't know celebs.
Yeah.
But actually, I've reached out to a few friends that work in LA, so you never know.
I did hear a talk show host say his son was a senior in high school this year. So maybe they're watching. If you have famous relatives, what the heck? Let's get them in here.
Yeah. If anybody knows any celebs, send us a note. We want them on AP Live. Thanks, you guys. Thanks for
Bye.
watching.
See you tomorrow.
Bye.